This is a promise that I wanted to keep. Matheus, vai lá.
Boa tarde, meu nome é Matheus. O título da apresentação está aqui. Agradeço pela atenção. Tchau.
You have a spokesperson.
Yes, he wanted to. So the story is, I at some point I felt sick and said I don't know if I can give the talk, and he said he's going to take over.
Okay. So
I wanted to get, but I promised him he could take over. So now that was a compromise.
He's not shy. That we can see.
Yes.
He's not shy.
Yeah.
So it is a pleasure to have Tobias Micklitz giving us a talk today. Tobias graduated and got his PhD from University of Cologne. Then he went for a postdoc at the Free University of Berlin, and from 2007 to 2009, and then another postdoc at Argonne National Lab in the United States from 2009 to 2013. And since 2013, he has been at Centro Brasileiro de Pesquisas Físicas. So today he's going to talk about Floquet systems sidestepping the bulk boundary principle. So thank you very much for agreeing to talk to us. The microphone is yours.
Okay, so thanks a lot for the invitation. So let me first state, like, the main idea in the talk that I want to present is that we want to propose a quantum simulator which can simulate the topological insulator surface states in isolation. And the outline is, well, first I review some concepts of topology, and there I hope to convince you that coming up with such a proposal is actually not as trivial as one may think. And so I hope I can convince you that this is an interesting problem. And so this will take maybe half of the talk, and then the second part of the talk I will come up with our concrete proposal for this quantum simulator. So this work is actually work it's still not finished, it's ongoing work, but hopefully we are going to finish soon, and it's done with the Cologne group, so it involves Kun Kim, who's actually right now has a position in Seoul already, and Dima Bagretz and Alexander Altland. So, okay, let me start out with some general, reviewing some general concepts. So, well, I mean, we all know that in the last years or decades, the ideas of topology, ideas coming from topology, have heavily influenced the physics in condensed matter, or our thinking in condensed matter physics. And there's different notions of topology, so I should be more precise what I am having in mind throughout this talk. And what this subject is related to is to the topological insulators, which is the gap phases of non-interacting fermions. So more specifically, it is related to the surface states that form at such gap phases of topological insulators. And well, it's these gap phases of non-interacting systems, of non-interacting fermions, that we also have a very good understanding, or actually a complete understanding of possible topological phases in these gap phases of non-interacting systems. So gap phases here refers to insulators, but also to superconductors, which have a gap for the excitation. So all this knowledge that we have about the gap phases of non-interacting fermions is summarized here in this table, and probably most are familiar with this table, but still I would like to spend some time to go through it. So what is shown here in this table is these are letters. This is 10. These letters denote 10 different symmetry classes, and this classification into 10 symmetry classes goes back to an old work by Altland and Zirnbauers in the 90s, who were just considering quadratic Hamiltonians of fermionic systems. So quadratic Hamiltonians here means that one can take into account interactions in some mean field form, like in superconductors, but in principle one talks here about quadratic Hamiltonians of fermions, which don't have to be insulators, but just general Hamiltonians. And what they found is that if we are considering condensed matter systems, then actually all systems that we are interested in, they can be classified into 10 possible symmetry classes. And this is like, let's say, the most general classification. Of course, if you have some special lattice symmetries or some other symmetries, this classification can be refined. But if we talk about just very general systems where we do not talk about any specific lattice symmetries or so on, then the observation is that one can classify all quadratic Hamiltonians of fermions into 10 classes. And the basic observation is that there's two fundamental symmetries which are important in these condensed matter systems, which is on the one hand time reversal symmetry. This would be the theta here, and then we have particle hole symmetry. Now these symmetries, we can actually associate three numbers. So there can be a 0, which means the symmetry is absent, and then there can be a 1 or a -1, which means that the symmetry is there, but the operator and the operator squares, the relevant symmetry operator squares to 1 or to -1, the same for the particle hole symmetry. So for example, for the time reversal symmetry, well, you can have a system without any time reversal symmetry, and if you don't have any particle hole symmetry, so you don't look at superconductors, this would correspond to this case here, where you don't have any symmetry, and this is class A, which is, for example, the quantum Hall insulator class. But if you have time reversal symmetry, then you can have two scenarios. So in one case, it can be that your spin degrees de freedom decouple, so that you don't have any spin-orbit interactions. In this case, the world of your spin up and down electrons, they just completely decouple, and you can just talk about the spinless electrons. So this would be the case where the time reversal symmetry operator can be simplified and squares to 1, and this would correspond, for example, to the class A1 if you just have the symmetry. So once you have spin orbit interactions, then the world of spin up and down particles do not decouple, and you have to take into account the full time reversal symmetry operator, it squares to -1. So this would be, for example, class A2. So in the same way, you can distinguish three possible cases for superconductors with or not having a spin rotation symmetry, and then you come up with 3 × 3 9 classes. So then the observation is that you can combine these two symmetries to have another symmetry, which would be the chiral symmetry. This is pi, and this doesn't give you anything new in case that you have either particle hole or time reversal symmetry. However, in one case where you don't have any particle hole and don't have any time reversal symmetry, so this would be class A3, you can still have this chiral symmetry. So this adds one other class to the system. You can come up with this, 10-fold classification. So there's some periodicity involved. So this is first of all the classification of quadratic Hamiltonians of fermions. Now, once Kane and Mehle came up with their discovery of topological insulators, so now topological phases of gapped such quadratic Hamiltonians, a natural question that came up was, what classes actually do allow for these interesting topological gapped phases? And this answer was given by Kitaev and Shinsai Ryo and co-workers. And this is then summarized in this table. So it turns out that the answer depends on the dimension. So now here on the horizontal axis, we have the dimensions. They go from 1 to 8 because there's some periodicity involved. So after dimension 9 is the same as 1. And now this table summarizes in which symmetry class, in which of the Alexander symmetry classes, in which dimension we can have interesting gapped, topologically interesting gapped phases of fermions. So 0 would correspond to the case that you just have trivially gapped phases. The Z here means that you have an infinite family of gapped phases. So D equals to 0 would be a trivial phase, but then you have also an infinite family of topologically interesting gapped phases that can be characterized by some integer winding number. Now, the 2 here means that you have two possibilities of having a trivially gapped phase or topologically interesting gapped phase. And these 10 symmetry classes can be organized in this nice way. So these two correspond to some complex classes, and these are real classes, and then there is this periodicity involved. So these two classes stay among themselves, so you have a periodicity always on these diagonal axis here, and there's some periodicity here, which is a Bott periodicity here also on the diagonal. So we come back to this later. So this is all our knowledge we have about the gapped phases this quadratic Hamiltonians. Now, if you have a topological insulator, it typically reveals its non-trivial bulk through the presence of gapless surface states. And to illustrate this, consider here some piece of insulator which is topologically interesting. So this is denoted here by this index 1, which corresponds to some interesting topological property. And this piece of insulator is embedded into the vacuum. So the vacuum is also an insulator, and in a way, by definition, this is trivial. So you have here, let's say, your space, and it's divided into one region where you have a topologically interesting insulator, and the other region space outside this insulator is topologically trivial. So in a way, the situation is very similar to having a donut, which is topologically non-trivial, and a Berliner, which is topologically trivial. So in topology, what we're talking about is deformations of objects. So for example, the Berliner can be just deformed smoothly into a point, and this is why it's topologically trivial, while the donut cannot be deformed into a point because of this hole, which makes it topologically non-trivial. So in topology, we talk about these deformations which have to obey certain rules. So you have to stick to the rules. Like in topology, you have to do smooth deformations. You cannot do any cutting or making holes. And that's why you cannot deform this donut into this Berlin into the donut, because you have to do something drastic, in a way breaking the rules of the, let's say, the rules of the game to introduce this hole here. And this is why there's no possible deformation from one into the other without so changing the topological number from a trivial to a non-trivial comes with doing something drastic. So the situation now here is very similar. Like the topological insulator here with the non-trivial index can be compared to the donut, and the vacuum to the Berliner. So now if we look at a path in space, let's say from the inside of this topological insulator to outside the vacuum, what we actually do is, by going along this path, we do change the topological winding number, or the topological index from one non-trivial to something trivial. And in the same way as we cannot deform the Berliner into the donut without doing anything drastic, we also cannot do this without doing anything drastic. And doing anything drastic means here that we break somehow the rules of the game. And well, what we stick to here was talking about topological phases, gap phases of fermions. So breaking rules of the game here just means that one has to close the gap when going a path from here to here. So we see that when doing a continuous interpolation between two topologically different insulators, here the vacuum and this piece of topological insulator, this necessarily has to occur via an intermediate metallic phase. So this means that in this case, well, you have to close the gap, and this will happen at the surface. So you have a metallic surface states at this topological insulator. And this is what makes them very interesting. So we see how these ideas of topology are very beautiful and very strong. I mean, it's very simple arguments, and this means that these metallic phases, they should be very robust. So if you put disorder, whatever, onto the surface, they should survive. So that makes them very interesting. So this is now a real space picture where we have this chunk of topological insulator. On the surface, there is these metallic surface states. And in K-space, they are described by some Dirac cone. And here's the energy relation. So we have here a band insulator with a valence and a conduction band separated by a gap. And then we have in between these dispersing bands, which, if you look at the eigenfunctions of these states, they are exactly these eigenstates are localized on the surface. So these are these topologically protected metallic states at the surface. And well, this is not only science fiction. I mean, there's ARPIS data which measure this Dirac cone here. So these surface states on this topological insulator, so the strong topological insulators, they are very interesting because they are robust against disorder. So you can also have a weaker case of topological insulators, which are not that strong, strongly protected. So this is if you have an even number of Dirac cones on the surface, or more precisely, like have pairs of Dirac cones with opposite chirality. Then if you add disorder to the system, so it's also nice that that you can have in these weak topology insulators. You can have the surface states, but they are not as strongly protected as the strong topology insulated states, because if you have an even number of these cones and add disorder, then typically they will couple and then just gap out. So they are not protected against disorder. So it's the odd number of cones, or if you have an even number with the same chirality, that are really protected against localization due to disorder. In this way, one can really talk about topological metals because they are topologically protected. Now, there's some theoretical questions on these surface states, but then there's also a practical problem. So if you look, for example, at the conductance data for the edge states of a 2D spin quantum Hall system, so in theory, these 1D channels should have perfect quantized conductance, but in the real samples, you'll see that the conductance is not perfectly quantized. And the reason for that is that, well, you have these topological edge states or surface states, but they're not, they don't live in their own universe, but they're coupled to the bulk. And what typically happens is that you have heat or electric currents that can leak away from the surface into the bulk. And that's something that is actually not very nice. So what we really would like to have is to have systems where we can, in a way, decouple the surface states from the bulk. So that's then the idea. Can we find a system where we can have only these topological metals that are the isolated surface states of topology insulators without having the bulk around? And one thing one could think of is, for example, Weyl semimetals, which are also much discussed in the last years. But there, what you have, the situation is, well, in the Weyl semimetals, you also have Dirac or Weyl fermions that now describe the bulk system. But what happens in these Weyl semimetals is that you will always have an even number of cones which opposite chirality. So it's exactly as the surface states of the weak topology insulators. And so if you have disorder in the system, then they will typically couple and gap out. So these Weyl semimetals actually are not what we want. And actually there's a reason why in these Weyl semimetals there's always appearing cones of opposite chirality. And the reason behind is the fermion doubling theorem, which states that a local real free fermion lattice action having chiral and translation invariant necessarily has fermion doubling. So people who are doing lattice QCD actually know this, that they cannot generate a single Weyl fermion on a lattice. So the statement is that whenever we look at condensed matter systems where we have some lattice involved, there's necessarily an equal number of left and right-handed Weyl fermions in the compact Brillouin zone. So that's in a way bad news, because the question that you just posed on the previous slide, well, can we come up with some system which just has the isolated surface states of a topology insulator without having the bulk? Well, this cannot be realized in any condensed matter system. So that then brings the idea that we can now state the question somehow more let's say, theoretical first. So the idea is then now forgetting about condensed matter or lattice systems, just the general idea, can we somehow construct these topological metals from Floquet operators? So the idea is, can we come up with some simulator for these topological surface states? So simulator here means really just the unitary operator here, which would be the time evolution operator. And what we want to look at is the discrete time evolution operator, which now mimics the dynamics of just the surface states of topology insulators in isolation. So can we come up with some Floquet topological metal? So can we come up with some simulator in terms of a Floquet operator that simulates these surface states of a topology insulator? And to explain this idea, we can first look at the simplest example. So later on, we are interested in more realistic such Floquet operators that really mimic the surface states, let's say, of higher dimension topology insulators and with disorder. So we want to see what happens then with disorder and so on. But first, to illustrate this idea, we can look at the first, well, at the simplest case, which would be a 1D system, a clean system. So 1D clean system, the time evolution, the Floquet operator is diagonalized in momentum, so we can just write down a unitary operator. In the simplest case, it's just a complex number with modulus 1. So in the simplest case, we can just write down a 1D unitary, which is e to the ik. Or we can write down something a little bit more complicated, which is I to the ek times sigma 3, which is a Pauli matrix acting in spin space. So in terms of just abstract, these are describing now unitary operators. So this is again the table which was for gapped phases of fermions, so described by Hamiltonians. Now I'm looking here at the time evolution operator, the discrete time evolution operator, again of a free fermion or quadratic system. In 1D system without any symmetry, so where the gap phases are trivial, and I'm looking here at this unitary class operator in 1D without any symmetry, or if one looks at this unitary operator, this would correspond. So actually there should be added a phase to break chiral symmetry, but this has some time versus symmetry. So this would be a unitary operator in 1D class A2, which doesn't have any interesting gap phases. But, well, if you look at what these time evolution operators do, well, this just propagates here in a chiral way, just in one way, a particle, and this propagates the particle depending on the spin orientation in one direction or the other direction. So we can see that what this unitary operator does is actually describes this one here, just describes the chiral edge states in isolation of a quantum Hall system, of a 2D quantum Hall system, just the one chiral edge state. And this would corresponding, or this would simulate like the discrete time evolution of a single edge of a spin quantum Hall system. So this means, well, if they simulate these topological surface states, we should see that they describe something topologically protected, so that they are simulators of topological metallic phases. And indeed, one can see this because this unitary operator and this, they are characterized again by some non-trivial topology indices. So this unitary just has a non-trivial winding, and this unitary has a non-trivial Pfaffian. So this tells us, or this here lets us know that this discrete time evolution operator also can be characterized by some topology. And looking at this table, well, if this guy here, this unitary mimics the surface state of this topological index, somehow we should expect that there's a relation between the topological classification of a system in D dimension in a given symmetry class. It should be related to the topological classification of gapped phases in one dimension higher. So if we have a topological insulator here, characterized by some winding of the Hamiltonian or the ground state, then in one dimension lower, there should be a corresponding topological classification of now metals, of unitaries describing metals. And actually, it's true. So there's some systematic how one can generate a topological classification of the Floquet operators, now mimicking metals, to the insulators in the same class in one symmetry higher. And this is now talking about topological classifications of unitary operators, which have popped up in different contexts. Probably in the first was in the context of scattering matrices, where one tried to relate the scattering matrix, which describes the scattering from a topological insulator to the topological insulator. Again, there one has to relate somehow the gapped phase in D dimension, the Hamiltonian, to some so topology of this to the topology of a unitary operator in the same class in one dimension lower. And the idea is as follows. So let's illustrate this for the class A2, for the Floquet operator that we wrote down that would mimic the metal at the surface of a 2D quantum spin Hall system. So one has this unitary operator, and the idea is that one can construct from this unitary operator now a Hamiltonian that describes a gapped system. And this Hamiltonian that one describes a system in the same dimension, however, has a different symmetry characterization. And actually, one can construct a Hamiltonian such that in this table, it describes a system in a class above the one that one is looking at for the unitary operator. So once one has constructed this Hamiltonian, then one can do a topological classification now of this gapped Hamiltonian and by the Bott periodicity of the periodic table, we know that the topological classification of this gapped phase in the symmetry class above the one we're looking at the same dimension is actually the same as the topological classification as in the symmetry class that we are interested in one dimension higher. In this way, one can relate the topological properties of the Floquet operator that should simulate the dynamics of the surface states actually to the topological classification of the gapped system in one dimension higher. And just to make this illustrated as one example, one can look at the class A. So this class A in one dimension that we said, the Floquet operator that we wrote down was just e to the ik, very simple. And we can construct from this a Hamiltonian which now has e to the ik and e to the minus ik on the off diagonals. So this is a Hamiltonian, and well, it's traceless, and the determinant is -1. So it just has two flat bands, 1 and -1. So this describes an insulator. But this Hamiltonian now has an extra symmetry. It only occupies the off diagonal component, so it has a chiral symmetry. So now employing the Bott periodicity like in the complex class, we started out from the Floquet in this class here, constructed a Hamiltonian which now has chiral symmetries in class A3, and the topological classification of this guy is the same as the topological classification here, and this is how we can see that the topological classification of the unitary in terms of the winding is just reflecting the topological classification of the insulator in one dimension higher. So with this in mind, we can now just continue like first with the abstract consideration. And we can just cook up some unitary operators in some d-dimensional system that now is characterized by some non-trivial topological index. And the game that I'm doing here is actually for two examples. So I discuss in more detail the first example, the second I just mentioned briefly. So the first example is the four-dimensional quantum Hall system. So this would be class A in 4 dimensions, which has a Z classification. So the question is, can we cook up some unitary operator that would now mimic the discrete time evolution of its surface states? So can we cook up some Floquet operator without any symmetry in 3 dimensions that has a non-trivial winding? And it turns out, yes, we can do so. So we can write down some unitary operator that now depends on three momenta. So this is still a clean system. Later on, we'll add this order. So we can write down a unitary that depends on the 3 momenta multiplied with the 4 Pauli matrices. Sigma 0 is the identity. And we can write down some parametrization, which now, if you plug this into the winding number formula, you get a 4, which would mean that this unitary operator actually simulates 4 right-handed Weyl fermions corresponding to the surface, to the surface state of 4D quantum Hall system at the 4th plateau. And if one looks closer at our example that we just mathematically constructed, one sees actually that there's one function, which is the absolute value of sine k, which is a highly structured function. And this now tells us why we could succeed. So because by the fermion doubling theorem that I mentioned earlier, we expect that we cannot come up with such a proposal in a condensed matter system if there's a lattice. And indeed, the example that we came up with here involves this highly, let's say, a structured function, which would, in a lattice relation, would just involve infinite range hopping, which you don't have. So we can come up with some abstract unitary that now escapes the fermion doubling principle because it just doesn't, it cannot be realized by some lattice system. So in the same way, we can come up with a protocol that can mimic or that can simulate the dynamics of the 2-dimensional dynamics of the 3-dimensional quantum spin Hall system. So this is all first abstract. What we would expect is if we have some unitary sum simulator of this form, if we now add this order, this should be very robust against this order, and in some cases it should show Reynolds diffusion. But so far this was all abstract, but the challenge now is to come up with some real proposal how this unitary can be constructed in some really physical system. And then the next point actually is that we would like to have some experimental platform where this can be realized. So this then brings me now to the second part of the talk, which is now where we want to put this idea of making a proposal for a quantum simulator that can simulate the dynamics of topological surface states in isolation more concrete. So to make this proposal concrete, well, the first thing is we have to see how we can actually come up with a physical proposal to realize this unitary, which was in a way a mathematical game on the previous slide. And as said, we cannot expect that this can be done in some lattice system. So the idea that we have is to use some idea which has been already used, which is to generate extra dimension from dynamical protocols. So to look at, in our case, 1D systems, which are driven externally by some incommensurate frequencies, which allows you to simulate the dynamics of high dimensional systems. And then the idea is that due to this dynamical protocols, you have more flexibility to design, let's say, the dynamics in this extra dimension, and you're not as restricted in a lattice system. So that's the first idea. Then the second idea is once we have come up with a concrete then time-dependent protocol, we should actually, so what we want to do then is add disorder and so on. So we should actually show that this protocol that we propose really does what we want, namely it simulates the dynamics of the topological surface states. And we show this by deriving an effective field theory, which corresponds to the one of the surface states. So that's the second point. And then the third point is that we actually would like to have our proposal be realized. And what we think may be a very good thing is to look at optical linear networks where this can be realized. So now in the rest of the talks, I'll just go through these three points. So I hope like that the motivation is clear, like what we want to come up is a quantum simulator for these isolated topological surface states. Now I'll get through these 3 points here. So let's start with the first thing. So as said several times, we cannot expect to come up with a Floquet operator that we want to in a lattice system. So we somehow have to overcome the fermion doubling theory. And our idea here is to use 1D systems that are driven by d-1 incommensurate frequencies to simulate the d-dimensional system. So there's a mathematical observation, which is if you take a 1D system, so here Hamiltonian for 1D system that is described here, let's say by one coordinate, which however is driven by some frequencies that are all incommensurate. So one has here d-1 frequencies that are incommensurate. Then this is actually is equivalent by some gauge transformation to, like, the dynamics of this guy is equivalent by some gauge transformation to the dynamics of a d-dimensional system, where actually due to the driving one can see that the system will be disordered in the artificially generated dimension by this driving. And this is actually something which is also in our favor because we want to really study realistic simulators for surface states with disorder. So the idea is to use this engineering of extra dimensions by driving with incommensurate frequencies, because then these functions can be chosen very flexible to generate something like this absolute value of sine, which you cannot generate in a lattice. So this engineering of extra dimensions, we want to use this in our favor to be flexible to escape the fermion doubling theorem. And actually this generating of extra dimension by external driving, it's not something, it's not science fiction, but it has been realized in experiment, for example. So here is just showing a very beautiful experiment done already a couple of years ago with cold atoms. And this cold atom experiment actually was the first very controlled study of a 3D Anderson insulator transition. So what was done in this experiment, they started out from a cloud of cold atoms in 1D, which was kicked by 2 incommensurate frequencies. And by this principle of the previous slides, the dynamics that you generate by kicking this 1D system with 2 incommensurate frequencies is just equivalent to the dynamics of a 3D system, which now has disorder. And by varying the kicking strengths, one can vary the disorder strengths. And in this way, they could, in a very controlled way, change the kicking strength or the disorder strengths and tune to the Anderson localization transition in the 3D system. And the very good control in this case allowed them to tune exactly into the critical point and then measure, for example, critical properties of the Anderson localization transition. So this idea of using the generation of extra dimension by external driving was crucial in this experiment to make these well, beautiful observations of the Anderson critical dynamics, for example. So in our case, actually, we need something a little bit more complicated, because in these cold atom systems, you typically do not have any internal degree of freedom. What we need here, which hopefully comes clear in in the rest of the talk, what we need is to have some internal degree of freedom. And this is why we think that maybe cold atoms, although they are working on it, may be more difficult, but optical linear networks that I come later to are more promising. So in this case, what we are talking about is 1D systems now of a Walker, which has an internal degree of freedom. So in this case, this will be just a spin 1/2 particle that is hopping on a 1D lattice. So you can have hopping to the right or hopping to the left, or you can stay where you are. And then the important thing is that after you apply any of these translations, you apply some spin rotation operator. And what you then need for our proposal is that you have a very good coherent dynamic control over your spin degrees of freedom. So the idea is that if you can now vary these spin rotations in some way using incommensurate frequencies, you can, in the same way as in the kicked rotor on the previous slide, can now generate by these time-dependent protocols actually or simulate the dynamics of high-dimensional systems by using as many frequencies as you want to generate as many dimensions as you want. And again, in these artificial generated dimensions, you typically have then disordered dynamics, so there's some chaos. You generate disordered dynamics. So using this protocol so this would be the unitary time evolution for a single time step. It should consist of some translation in combination with internal rotations, where the internal rotations are now varied in time using incommensurate frequencies. And if you have great flexibility how to choose these time dependencies, then one should be able to overcome the fermion doubling theorem. So our proposal now is that we come up with a 1D walk with time-dependent rotation axis, which mimics these unitary operators that we mathematically introduced on some previous slides ago, which have these non-trivial windings. So by gauge transformation, or by gauge, the transformation, the dynamics of this should then be equivalent to the Floquet operator that we had before discussed for, let's say, for simulating the 3D surface of 4D quantum Hall system or the 2D surface of a 3D quantum spin Hall system. And well, it turns out that for the 4D quantum Hall system, the walk that you have is actually quite simple. So this is now the idea of using the 1D quantum walk with time-dependent rotation axis that, upon gauge transformation, simulates equivalent dynamics to the Floquet operator that we introduced in the previous slides, that simulates the 3D surface of the 4D quantum Hall system. And this is a protocol, what it looks like. So it is just chiral hopping. So you either hop to the right or to the left. And you hop to the right if you are in spin up position, and you hop to the left and you're in spin down internal position. And what is spin up and spin down is defined via some spin quantization axis that is now varied in time. So you have chiral hopping with respect to some spin quantization axis that is varied in time using incommensurate frequencies. So these are the two incommensurate frequencies, and the exact protocol how you should vary this time-dependent quantization, spin quantization axis. Well, this now involves exactly this absolute value of sign, which we wanted to have. So upon gauge transformation, this is just a Floquet operator that we introduced, that we showed, that has a winding number 4. So it would simulate the 4 Weyl fermions of the surface of a 4D quantum Hall system now with this order. So we can okay, so with this order we can come up also with a similar proposal for a protocol for mimicking the Floquet operator of the 2D surface of the 3D spin quantum Hall system by some time-dependent protocol on 1D Walker, which is a little bit more complicated, but we can do this. So this completes our first point that we wanted to make, namely to come up with an idea how we can overcome the fermion doubling theorem. So the idea is that we now have these 1D walkers with some time-dependent, say in the example of the quantum 4D quantum Hall system with a time-dependent spin quantization axis that should be able to simulate now the surface states of the 4D quantum Hall system. But now we add this order and so on, so we should really show that actually the dynamics that we simulate by this dynamics of the Walker is what we want to have. And the way we do it is we can derive an effective low energy theory for this protocol. So for this 1D Walker with the time-dependent spin quantization axis, we can derive some effective field theory that now describes the dynamics of this Walker on long, time, and length scales. And we should find that this is the same field theory as the one for the surface states of the 4D quantum Hall system. So that's what we're doing. So we apply some field theory machinery starting out from the time-dependent protocol of the Walker to derive an effective field theory. And this is the effective field theory that we find. It's known as the nonlinear sigma model, and it's in a way the standard model for the disordered single particle systems. So it predicts an Anderson localization in dimensions smaller than 2 and then localization transition in dimensions larger than 2. And the way to derive it is, well, we apply the gauge transformation to transform the time-dependent protocol into some equivalent dynamics, which is not time-dependent, but now is in the quantum Hall system in the 3-dimensional space. And then we apply some usual steps in the machinery of the field theory of disordered systems to arrive at this action. Now, obviously, this cannot be the end to the story, because if this was everything we find, then we failed, because this action would predict Anderson localization transition for strong enough disorder. But what we actually want to mimic is the surface states of a topological insulator, so this should be robust against Anderson insulator. And the nice thing is, when we go through these standard steps to derive this effective field theory, we see that actually an additional term pops up, which is a topological term. And this topological term is a Chern-Simons action, and it has a coupling constant, which is exactly the winding number for the Floquet operator that we introduced. So this pops up here nicely, just in the derivation. And the Chern-Simons action is actually exactly the action that has been previously identified to describe the surface states of the 4-dimensional quantum Hall state. So by this, we show that the low energy physics of the protocol that we propose is indeed now with this order and everything is indeed what we wanted to. So then we can actually do a similar derivation also for the second example, for the 2D surface of the 3D quantum Hall system. And by this we have now at least, let's say, a physicist will not prove, but we have convinced ourselves that the protocol that we came up with that escapes the fermion doubling theorem by this idea of using time-dependent protocols, that this is really generating the dynamics that we want to. So now in the last step, we should actually come up with a proposal for an experiment where this time-dependent protocol can be implemented. And the idea that we have is to use optical linear networks. So this is now the last part. So on the optical linear networks. So in these optical linear networks, what they can simulate very nicely is this walks, quantum walks. So actually, they simulate very nicely these 1D quantum walks that are described. Again, here's a Floquet operator of a single time step evolution, which consists of two parts. So one has a step operation and a coin operation. So the step operation is just chiral hopping to the right or left, depending on the internal degree of freedom. And then the coin operation is just a rotation of your internal degree of freedom. So a single time step operator consists of translation and then rotation of the internal degree of freedom, and applying this iteratively, you generate this quantum walk. So in these optical linear networks, the walker are photons, and the spin 1/2 degree of freedom corresponds to the spin polarization. So for example, the step operation is done in this feedback loop. So what one has, one inserts the photons into some loop here, lets them pass to a beam splitter, which now separates the photons according to their polarization orientation. Let's say the vertical polarized goes up here, and the horizontally polarized light goes here. And then one just sends these lights to long cables. And these cables are such that one is longer than the other. Let's say one is 1 kilometer longer than the other. And then once you recombine these two clouds of photons, then they will be separated in time now, corresponding to whether you have vertically or horizontally polarized light. And then you can put this again in the feedback loop and iterate this. And if you iterate this, this corresponds to just iterating a walk without rotation here, just a chiral hopping on a lattice, where the lattice is now actually what you have here in time. Then they have here this electro-optic modulators, which they can turn on to just break through this feedback loop and send then the photons into observation unit. So this would how they do this step operator. And the coin operator is done by polarization plates. So by these polarization plates, you can just rotate the internal degree of freedom. And the very nice thing is that they have a very good control, dynamical control over the axis of the polarization rotation. So there's been some recent progress which allows them to do very fast switching of these rotation axes. And that's why we hope that in this setup now you can implement by designing these control voltages the time-dependent rotations that we want to have. So just here's an example of such a quantum walk experiment that was done in the group von Christiane Silberhorn, where they studied, for example, Anderson localization in such a system. So they had a walker, chiral walker, and then the rotations which can mimic the disorder. They studied 3 scenarios. So in one case where this rotation of the internal degree of freedom was just constant, this translation invariant system, then where it was spatially varying, or simulating a spatially varying rotation and some dynamically varying rotation. So in one case, you just have translation invariant system, you have ballistic dynamics. In the case where you mimic static disorder, they could observe Anderson localization. And in case where you have dynamic disorder, you have just classic diffusion. So there's experiments where they already observed Anderson localization. So the idea is now, I mean, obviously it's harder, but the idea is that if they can use now these rotation matrices and make them time dependent by using the right voltages, hopefully they can implement the protocol that we propose. Actually, we came up with some blueprints how, for example, the 4D quantum Hall system can be simulated in such an optical linear network. So essentially, these are the 2 feedback loops, which now are just the chiral translation to the right or left according to the spin quantization axis. And this is a combination of rotations that you apply to dynamically change the spin quantization axis, which now has to be modified in this experiment in all time steps. Similar, we can come up with some proposal for the 2D surface states. Actually, we have right now, if I can make some advertisement, maybe we have right now ongoing work with the group by Christiane Silberhorn. So we have some proposal for quantum walk experiment where we proposed to study the critical dynamics at an Anderson localization transition. So using this now here specific network, optical linear network, And they are right now working on this experiment, and so we have contact to them and actually now scheduled, I mean, some meeting to discuss now the walks that hopefully can be implemented to mimic the dynamics of the surface states of high dimension insulators. So this will be more difficult than our proposal here, but hopefully, yeah, this can be done. Okay, so this is then the third, as a check on the third point, which was a proposal for an experimental platform where one can implement what we would like to. So this brings me to the summary and outlook. So I discussed a proposal for a quantum simulator that can simulate the dynamics of topological surface states in isolations. The proposal is based on 1D quantum walks with time-dependent protocols, where the idea of using time-dependent protocols was used via generation of extra dimensions by driving these incommensurate frequencies, which allows you to overcome the fermion doubling theorem. We convinced ourselves that the low energy, so the long time and long length scale physics that is simulated by the walk is really what we would like to have, and we have some experimental candidate to do this. So next on the list is, well, we have to now seriously talk to the experimentalists if they are willing to really put some effort into this, to realize this. And of course, we should then, I mean, our field theory is only an effective description for the very long time and long scale physics, so we should identify good observable that this can be studied on reasonable timescales. Like in this walks, they can, it's varying, I mean, between 20 and 30 time steps. They can simulate this as shown in the previous slide in the experiment. They can see Anderson localization, so a natural candidate, of course, would be to implement this protocol once with winding 0 and once with a finite winding, and then crank up disorder and see that once one localizes the walk and once not. But yeah, maybe we can come up with different observables. This is all what we have to do, and then wait and hopefully see that at some point this will be realized. And yeah, with this, I'd like to thank you for the extension, for the attention, and thank to the CNPK and FAPERJ for support. Okay.
Tobias, thank you very much for a very, very nice talk. I forgot to mention the Outland-Zimbauer
yes.
periodic table. By far the best explanation I have seen. Thank you.
Okay.
Thank you so much.
Yeah, I have to know this.
Yeah.
Grew up with,
yeah. But it shows. It shows. It was very clear. It was very clear. So we are open to questions. Any questions from the audience? I have Eduardo. Can't hear you. Doc, can't hear you. He's having some technical problems. I see that he's very upset and frustrated. Do you want to type? You type your question and I read it. Okay. So while he is typing, I have two questions. You showed that the conductance of the supposed state in the surface shows that there is some leakage to the bulk.
Yes. And
this leakage should not occur if there was no coupling. And supposedly the system should have no coupling, and disorder shouldn't promote this coupling. So the idea is to completely, So the idea is to create a system that exists independently from the bulk, if I understand.
Yes.
If I understand the idea.
Exactly.
So, but my question is, how This system has exactly the same properties as the surface state, exactly. So you don't expect to see anything different.
So that's why we went through this Hazel with the field theory. So we can see that the low energy effective theory is just identical to that in this case of the 4D quantum Hall state.
Okay.
So it's a topological field theory. And if we believe in that this captures the universal properties of the system, then, well, it's the same universality class. I mean, if you go to details and whatever, of course, but let's say the protocol is in the same universality class as the decoupled, like, of the surface state in isolation. So if you take your quantum Hall system and somehow get rid of the bulk and just maintain your surface states, this would be described by the same field theory as our protocol. Mm-hmm.
Okay. So you don't expect any new physics to emerge?
Well, there is this and this. Okay, so there's two things. So first, this is about the universal properties. So in the protocol, in the experiment, they will address shorter timescales. So there will be some non-universal properties. So that's why we should run the simulations. But then, I mean, that's the question what you call new physics. Like, for example, there's still, like, even in the quantum Hall system, there's questions, right? I mean, what is the real field theory for the topological critical point? And then there's some puzzling recent numerics about surface states of topological insulators. So even these systems it's not completely clear if the field theory is right and so on. So there's some questions on this which hopefully can be studied. Yeah.
Okay, and so could be even tested by the experimental setup that you guys are trying.
That would be great. I mean,
that would be nice. Yeah, that would be nice.
Yes.
So thank you for the answer. Eduardo has typed his question. If you could read it aloud for us and.
So this is two questions, right? Two questions. First, you mentioned that the failure to detect perfect quantization in the quantum spin Hall experiment is due to coupling to the bulk. But doesn't the theory predict the decoupling? What aspect of the theory does not correspond to the real material? So I guess the answer here is if you would have a perfect insulator with a large gap, then everything is fine. But typically, I mean, these topology insulators, I mean, don't have a perfect gap. I mean, the gap is not that large. Then you put disorder and you just inevitably couple the surface states to the bulk. That would be my understanding. So the second, in the effective field theory, the topological term destroys endless localizations. That's right. You mentioned that it should describe a robust surface state. Yes, it's a topological term that makes different from yes, exactly. I don't know. I mean, about the non-perfect quantization. I mean, there have been, I guess, other talks also here. But my simple understanding is this, right? That the gap is not large enough. You put disorder, you have a coupling. That's why you. I mean, there have been these experiments by Molenkamp in the beginning. They show quite nice quantization, but as what I heard always is that not so many groups were able to reproduce this, for example. So I'm if anyone is more expert, please correct me. But that's my impression, yeah. Mm-hmm.
Okay, Edson, do you have any questions? You always have a question. Nope.
Yeah, I do. But I'm not sure you're gonna hear me. Can you?
Yeah.
Oh, good. I had a problem with my internet connection, and it must a while to come back. And I hope the recording will not be to have any problem. So my question is very basic, I have to say, and it's regarding the Fermion doubling problem. And I think the first part of your three items you discussed. So my basic understanding of Fermi doubling problem, when you have one V system, for instance, when if you plot the dispersion E versus K, so have, if you expect one Fermi point, you get two or
yes.
so on, right?
Yes, yes, you get
so,
you get an even number of these Weyl fermions. Yes.
Right. So if you calculate transport, for instance,
right,
you get twice as much for conductance, for instance, right?
Yes. Mm-hmm. But the problem here is that you have always like the Weyl fermions of different chirality. So if you put disorder into the system, this is not robust, right? So you put a lot of disorder, they will couple and they will just gap out. So it's like the situation with the weak topological insulators, where you have an even number of Dirac cones in the Z2 class. So they are in a way nice, and there has been some dispute how strong and whatever they are. But if you're really interested in a generic system where you can now put in a lot of disorder and see the dynamics, these guys will gap out. I mean, the question is what is exactly disorder strength, but they're not topologically protected. It's not, I would say it's not the topological metal in the sense as the surface states of a strong topological insulator in isolation. It's
it makes sense. So,
yes.
But the second question, if George is not really perturbed with that, so do you have like a simple picture for the role of the extra dimension when you add these time or this frequency?
Yes, it's like maybe best in the kicked rotor. So in the kicked rotor, you have like a 1D particle, like that is like propagating on a circle, and then you start kicking it with some, let's say, one frequency or two incommensurate frequencies periodically. And what you can really see is that the dynamics that you generate, so you can make it first a mathematical trick. So you can make some gauge transformation where you gauge out the time dependence, but do this by cost of introducing some extra dimensions. So you can see that the dynamics is equivalent to the dynamics in a 3D system, which now describes a disordered system. And this is what they used in the experiment. So what you have then there is a 3D system. I mean, the physics is the same as in a 3D system. But of course, it's a little bit different. Like you don't really have Anderson localization, but it's called dynamical localization. So what you have there in this kick rotor experiment is that you have localization in momentum space. So you diffuse the momentum space. You in a way don't have energy conservation. But then due to the same quantum interference as you have in a disordered system with real space disorder, you get some localization. So quantum interference will hinder the system to expand in momentum space due to quantum interference. And the physics is exactly the same as that of a disordered 3D system, like with disordered potential in 3D. So this is the analogy there, and it's just like the general observation that you can mimic the dynamics of the higher dimensional systems through these extra frequencies. I don't know if this helped, but it's really like like in the kicked rotor, you have the dynamical localization momentum space, which is just the same as Anderson localization, and the space dimension depend on how many frequencies you use, incommensurate frequencies to drive the system. And I think this experiment is really beautiful. I mean that it's 2008 or whatever, so it's already some time ago, but it's really beautiful. Yeah.
So essentially, when you need to you make a change of reference frame, and then you need to rotate your spin accordingly just to keep the same physics, essentially, right? So that's why you need the two operations.
So in our proposal 4D quantum Hall system, we do the chiral hopping to the right and left. But what is hopping right and left depends on what is spin up and down. And spin up and down, we define with respect to a spin quantization axis that we then do in a time-dependent protocol that we use by driving with incommensurate frequencies. And again, you can just mathematically perform now a gauge transformation on this Floquet operator, which eliminates all the time dependence at the cost of introducing extra dimensions. And in this way, the dynamics is the same. Yeah.
Good. Thank you very much. Very nice talk, by the way.
Very nice talk. Very nice talk. And thank you to your son too for the introduction.
Yeah.
And I saw that he was whispering all the answers to you.
Yes.
And he will be invited soon for this.
Yeah.
Yeah. I let him know.
We see here that there is another question. Tobias, if you could read the question and.
From Tanya. Hi, Tanya. Nice to hear you. I do have a question as well. With all these difficulties to implement those states, have you thought in the applicability? For example, so if you can implement them, can you gain anything from it in topological quantum computation or spintronics? Yeah, good question. I mean, if one can really simulate them, then they have nice properties, but we didn't have so far. But it's a good question. Yes, that would be then. So if they can be simulated, one should think what to really do with them, right? You're right, I guess. Yes. Yeah.
So you could. You could create an isolated Majorana fermion, right?
Right. In this class, yes. Yes.
Yeah.
Yes. I hadn't thought about yes.
That would be interesting. That would be very interesting. Yeah.
Yes.
We could beat the high energy guys in this race.
Yeah.
But then you need to move down your index class table, right?
Right. I mean, I just focused on the 4D case, or quantum Hall and 3D spin quantum Hall. But in general, I mean, one just has to work out the protocol. So there's one thing actually that we realized. The one class you cannot realize is chiral classes, but this has to do with this gauge function. But particle should, one has to think about it, yes. But in principle, I mean, yeah. So the idea would be to come up with some abstract Floquet operator, which cannot be realized on lattices, and then see if this can be generated from a 1D quantum walk. Yes, one can try to do so for yes. Yeah.
So, any more questions? Any more questions to Tobias? So if not, we should thank Tobias again. Eduardo is writing.
And Caio too.
Caio, okay.
It's gone.
Okay.
Thanks for very, okay. Everybody's saying thank you, so thank you very much. I saw that Eduardo sent me an email saying that he was having difficulties to hear, but we're gonna be posting the talk on our YouTube page. So if I just in a second I can post this again. I did that last week. I'm gonna grab this address here. Just a second. Here. So, well, obviously it's not there yet because we just finished. But Edson has been very good at posting the talks. So tomorrow or maybe at most on Monday it should be there. So if anyone had problems with the phone or whatever, just check there tomorrow or Monday or in the weekend. So thank you again, Tobias, and
thanks a lot.
And stay safe there in Rio.
Okay.
Okay.